Hey guys, so welcome to our presentation. I'm honored to be here to presenting at StuySplash. My name is Farhan.
My name is Adam.
And my name is Jacob.
And today we're here to present on programming. So over the season we had lots of issues, to say the least. And we try to mitigate a lot of this with using maybe unique methods of solving some issues we had. We want to go through, we're going to go through a structure of showing maybe like a problem we had, and we're going to go through a solution set on how we basically solve the issue. So yeah, let's go into it. As I was just speaking on, it's basically just going to show some unique solutions. I think not many other teams have used. So we're gonna get straight into it. So after this season, we kind of went into the off season with a new doctrine of writing code and building robots. We want to design a system that's so robust that a toddler can drive it. Well, hopefully not literally, but it's your system should be so easy to use and so robust that like you could sub in anyone. You don't need to like teach them rocket science to drive a robot. You need to keep your cognitive load on the driver as low as possible so you're able to win and be as consistent as possible. That's basically it. So we're gonna go into our first problem. Imagine, how many of you guys actually program here? How many of you guys are you guys all programmers? Okay, so I'm gonna skip a little bit of the preface because almost everyone here should have programmed an elevator, right? With this year's game, we have to find a set point. So if you want to score L1, L2 up in your floor, you set the set point where you want to go to, right? And that relies on two things. Your robot has to have a constant starting position. So let's say you get, let's say you want to score on L2. Your height, your set point which your elevator will go to will be constant. And that means your position of the robot has to be constant. But that, like we said, that's adding more cognitive load for the driver. Your driver has to make sure that he's perfectly aligned to the reef and this and that and that. We're gonna go into something called elevator interpolation. And how many of you guys know what interpolation is? You? Okay. We're gonna go into the kind of a little bit of the math on the next slide, but basically, we're able to, let's say you have a coral in front of the reef. You can't be flush to the reef, right? Because you have a coral blocking it. You're able. So this system basically just, depending on how far you are from the branch, it'll move the elevator up and down to compensate. So let's just go into the video so you guys understand what I'm talking about. So here we can see we're not flush against the reef, and depending on how far we are from this branch, you can see your elevator is dynamically switching between how high it is and how low it is. Going back to the constant, like if you have a constant set point, let's say you set your distance from the reef when you're flush against the reef, you get that set point and it'll only work when you're in that position. Let's say for whatever reason your auto alignment is not perfectly aligned. Like we had, I guess, some angle issues with our auto line, and that would mean we're not flush against the reef. So this system will basically just remove that error, and you're always able to hit a shot. Once again, we're using linear interpolation to do this. You could use calculus, but we found linear interpolation the easiest. You can use related rates in calculus, but linear interpolation is just the easiest because you're able to just get a data set. You just test different numbers and you put it in a table. And once you put it into a table, you get a graph like this. So this is basically your linear interpolation equation. And to get into what interpolation really is, it's really just you have different data points, and inside of and you have to predict for any input. So let's say you only test, so here, you only have a point for when we're 4 inches away from the reef, and we add an offset of 0.5 rotations. So for just for some context, most people, they usually convert their set point from motor rotations to meters. But for the sake of this, we just use rotations. It might be a little bit more annoying if you want to do some like extra stuff with that, but we just convert like when we need to do when we need to use it in an equation anyways. So besides that, we see that we had 3 points. So we basically just go on the reef and we basically just test out. Let's say here when we're 0 inches away from the reef, that means when you're flush. When you're flush, you don't add any offset. You just use the offset when you're at that position, right? Does that make sense a little bit? Yeah, so you don't add an offset. But as soon, our next point that we found is when we're 4 inches away, and when we're 4 inches away, we add 0.5 rotations to that offset. So if we go back to this video, like let's say when we're 4 inches away, your default, your constant set point when you're here, you're basically adding 0.5 rotations to your set point when you're 4 inches away. So that's really what I'm trying to get at. We still have a constant set point, but we're adding using the interpolation. We're just adding more distance to go higher and higher, depending on how far you are. Yeah, so we have 3 points, and yeah, so using these 3 points, we're able to get any distance, and we're able to get any offset. Questions so far? Yeah.
How do you get distance from the reef?
So we're gonna have a code snippet, and we can show you. But you just use odometry, because you know where the reef is. You know where your robot is.
Yeah.
You would you just calculate where your claw is. Like you would add an offset because your odometry is in the center of the robot, right? Once you add that offset, you just find how far the branch is, right? Something we'll get into in a little bit is, since now your distance is changing, your initial velocity when you shoot the shooter has to change. And we'll show you how we get our range using that. Any other questions? So, kind of spoke on this. This is a code snippet. So we, in WPI-lib, they have, you don't have to write the math yourself. Like WPI-lib has amazing wrappers for basically all complicated math you can really use. So we use, it's called double tree map interpolator, and we didn't show the implementation, but you basically, this is just showing like us making the table. So like we said, your first parameter is going to be your distance away from the reef, and your second parameter is going to be how high your elevator should go up to compensate for that distance. So why do we choose 4 inches? Because the coral is actually 4 inches in diameter. So this perfectly models, like let's say your reef is here and you have a coral. Your robot cannot be flush against the reef anymore. So you add this offset to be able to score it even when your coral's in the way. So you don't have to like spin your robot around to like knock the coral out of the way. Right? Does that make sense? A little bit. Okay. And then we just add 5 inches away, and basically if you're further than 5 inches, you probably shouldn't even attempt the shot. And we found our own max value, which obviously depending on your robot architecture will be different, right? So yeah.
So can I just ask a question?
Yeah.
Maybe I missed it.
Yeah.
You're trying to adjust the drivetrain distance from the reef, or are you adjusting your actual height of your elevator?
The height of the elevator. Yeah. Does that make sense? Yeah. So you're basically, if you think of it this way, your input will be how far you are from the branch, right? And your output would be how high your elevator should go up to compensate for that extra distance. Does that make sense?
You're constantly setting that updated set point. So as you're getting closer, the elevator is actually slightly moving.
Yeah.
If you're 2 inches away, it's here, and you inch closer, and the elevator's automatically going through.
Right. Well, if you inch closer, it'll actually go down.
Oh, okay.
Right, but like if you go further away, it'll go up and up and up. Right? Does that make sense? Yeah. If you guys are a little bit confused, we'll have a video coming up like in a second, but we're gonna show like the full implementation, I guess. Yeah. Sorry. Yeah.
So yeah, I was just building off what he said. So it's like, it's kind of like, it's like a feedback loop that's like, it checks how close it is to the reef and then adjusts the elevator height based on that.
Yeah. Exactly. Yeah. It is. Yeah.
How do you do that? You do like, how do you like tell the difference between you and the reef?
Oh, we're gonna go into that right now. So, looking at this, should run just tells you if you're running the PID loop. And then we check if our desired goal. Okay, so L4, for context again, L4 is the highest height of our robot, right? You can't really go higher than L4. So obviously we don't want to like go higher than our max height. So we're checking if we're scoring L4 or L1. Because L1, you don't really have to go that high. It's just something we found. We have a toggle which just tells us if we're going to use this feature or not. And then once we go into that, we are calling our interpolation map once again. And this is where we actually get our distance. So I think you asked that question, right? Or yeah, you asked. So we have a function in Swerve called getPose, and that just returns a pose 2D. So that just gives question.
Can you just go over?
Yeah. Sorry.
Thanks.
So getPose just returns a pose 2D. I'm sure if you program, you guys all have used the pose 2D. Yeah. And then we get translation, which is an XY, and it gives you a function called getDistance. And we call this other static class called reef util, which basically just tells us information on where the reef is on the field in our system. And we basically just check the closest coral branch, and we got the score pose, which means the pose your robot should be at to actually score the coral. Because as we said, our constant set point is when the robot is flushing against the reef, right? So we're basically comparing that distance, our score pose, which is where we should be, to wherever we actually are right now. So depending on that distance, we will call our interpolation map, which will go back to this equation, and it'll give you how high your elevator should be to compensate, right? And like we said, let's say you're at L4, your elevator cannot go much higher than your max height, or else it's going to break. So before we set any set point, before we break anything, we basically have we have clamps. So does everyone know what a clamp is? Yeah? Okay.
Wait,
So yeah?
Sorry, I don't think what it is.
Yeah, okay. So a clamp is basically you have, let's say you have a number, and you're just basically clamping it in some interval. So this is the number, so your desired goal, which is your goal is like your set point, if you use a profile, right? So your goal plus your interpolator value, which tells you your new set point, and you're basically clamping that between like the static score position, which means like you shouldn't go below like your static score position, because you wouldn't need to. So that's your minimum value, and your maximum value will be how high your elevator can go.
It's just stopping it from going like higher than a certain number and lower.
Yeah, exactly. It's just an interval. Like you have to be in between this interval. And yeah, so as soon as we do all these safety checks, we can go into actually setting our goal. So we set our trapezoid profile state to this goal, and we set our goal because your goal should be zero velocity. So that's where you want your system to be at this position at zero velocity. I know this is a lot, but if you have a question, just feel free to stop me. Does anyone have questions before we move on? No? Yeah?
How do you implement get closest coral branch?
Well, that's like, well, you can always look at the code, but that's not the scope of this presentation. We're kind of just trying to get a general idea of some of the things we did. But if you're always free to look, our code is always public. You could always just look at our code and then see how it works. But like, we just want you to understand like how this feature was, not like, oh how does the pose work, or like stuff like that, right? Yeah. So any other questions?
What is a goal? What type of object is
A goal? It's a trapezoid profile.state object. So it's another part of WPIlib where are you familiar with motion profiling? Somewhat. Okay. So this is I'll answer it, but this is
there's goal there, then there's inputs.goal. Sometimes it's the same type.
Oh, okay. So we use something called Advantage Kit. It's basically a logging framework, and inputs is basically where you log your data. So what we're basically doing is we're logging this goal data value, and then we set it here, and your trapezoid profile, which calculates your set points, your profile, like your motion profile to get there, takes this object. So we're basically just this. So this is position, this is velocity. You're just basically telling it that you want to be at this position. Like you're basically just changing your data so your trapezoid profile will understand. Does that make sense? Because for a programming thing, you can't just put data types it does not want, right? Any other questions? There's our video. Okay, there you go. Hopefully you saw it too loud. So we're gonna show this in action. So we before wait, what is happening? Sorry guys, something's wrong with the audio. This should be it. Okay. I guess we're not having audio. Okay, whatever, it's fine. So this is a scenario where this will be seen as useful. We have a coral in the way. Jeez. 1 second, guys. Okay, I'll just explain while the video loads. Hopefully it loads. So you have a coral in the way, right? And like I said like a million times already. Okay. If your constant set point relies on you being flush against a reef, but now you have an obstacle in the way where it's not possible to I don't know what's happening with the video. Not possible to be in that position. So you either waste 2-3 seconds of your cycle spinning the robot or moving the coral away, or you're able to use this solution, which okay, the video's working. So. Okay, sorry guys. Or you're able to use a solution where it will just compensate with the height and you're able to shoot. I really want to show you the video so you guys understand what's happening, but that's not. I guess we're moving on. We'll get to the video if it does break. Later.
It's changed the sound twice. I think it's trying to play on the speakers of the switchboard or whatever it is, but it's not working. I could go work.
Oh, there you're right. All right, there you go. So you can see the elevator is dynamically moving up and down, and you're able to make that shot. So yeah, you can see it moving up and down. Yeah.
For this, is it detecting that there's the coral in front of it, or is it just
I was just gonna get into that.
pushing?
Yeah. So are you guys? So you're able to detect if something's in the way if you're drawing a lot of current. So so in our auto line, the way we check is our initial pose will try to be flush to the reef, because that's gonna be your best case scenario, right? If you detect that your drivetrain is drawing a lot of current, that usually means there's something obstructing the way. So your motors are drawing more current to run at that velocity. So as soon as you see your current is drawing more than it should, you should be able to estimate, or you have a good understanding that there's something in the way. So we use current sensing to be able to see if there's something in the way. And depending on that, we'll change our auto line set point. Yeah?
So the elevator can work. Does like the operator still have access to controlling the elevator? So the elevator can work by itself, so it's autonomously.
Basically autonomously, yes. You're able, if something really goes wrong, the drivers are always able to turn off all the automation we have, but we never, well actually we haven't been able to go to off-season comp because something happened with our team, but yeah, you're always able to override, because if something goes wrong, you don't want to be completely stuck in a match. But we've never had that issue so far in our testing.
But another question: how do you tell how close your road is to the reef?
To the what?
To the reef.
Odometry?
Odometry, yeah. So you use odometry. Do you have an understanding of what odometry is? It basically just tells you where your robot is on the field. We don't really have time to explain what it is. Yeah, but there's always there's so many resources you can use to learn. But for this type of understanding, like we kind of expect a little bit of understanding. So if I brush off a question, don't feel offended. Because we have a lot to cover, basically. Yeah.
Can I explain?
You could explain.
Okay, so vision so basically uses like AprilTags to see where you are, but odometry uses like the movement of the wheels, like based on like the current starting position, to see like where the offset is.
That's good. That's what I assumed it was, but I explained it. Okay. Thank you. Alright.
Can I just ask, where do you use, you're showing us this tool, do you use it only in the auto mode, or in teleop your driver clicks a button to automatically score? You're a few feet away, they click a button?
Yeah, so we do it in teleop. In Auton, we only score L4. Yeah, like we said, can't go much higher than that. Yeah. But yeah, we basically, we just press one button and it does that entire sequence. It auto lines, it does everything. It does everything automatically. So yeah. Now we're on to our second problem. So I'm gonna hand it over to Jacob.
So, as Farhan discussed, now we're able to change our elevator height based on the robot's distance from the reef. However, changing this height does not guarantee a consistent shot, because let's say you're like really far away and then you shoot the coral like very slowly, there's a chance that like the coral won't exactly make it to the branch and miss. So as you can see, we said a fixed shooter speed only works at one distance. So in order to circumvent this problem, we have to change the initial velocity of our coral every time we also change the height of our elevator. So
Wait, before we start, how many of you guys took AP Physics 1 or like you? Okay, so I think so. Hopefully we can understand a little bit of what's happening. This is just basic kinematic equations, but yeah.
Yeah. So first we start off with this kinematics equation, which gives you like the height as a function of time, right? And obviously we can't really do much with this equation because we don't know the time it takes for the coral to go from the claw and actually reach the branch. So logically our next step would be to find time in terms of constants that we actually know or constants that we're going to solve for. So here we use the equation velocity equals distance over time, and we rearrange it to solve for time, and we get time is equal to the distance that the robot is from the reef divided by the horizontal component of the initial velocity that we're going to give to the coral. And what we do is we plug that back into our first equation for all values of t, and we get this big equation. And you might be wondering, like, what are we going to use this equation for? So in our next step, what we do is we just rearrange the equation and solve for our initial velocity in terms of how far the robot is from the reef and how high the elevator is, because those are the two factors that will impact how fast we need to shoot the coral for it to actually reach the branch. Does anyone have any questions so far? Okay, so now we're gonna implement this equation in our code. So obviously the first thing we need to do is we need to define all of our constants. So we see theta is negative 35 degrees because our claw is angled 35 degrees below the horizon. R in this equation is just the distance from our claw to the branch. H is, so the way we solve for H is we find how high our elevator is from its original position, and then we add the distance that the claw is from the floor, which is this constant. So can you go back to the image?
Yeah.
Yeah. So H, the H in this picture is the distance that the claw is from the floor, and the way we find that is, well, what I just said, the elevator height plus the distance the claw is from the floor when the elevator isn't up at all, right? So, and then Ks is needed to overcome static friction in our claw. And
It's just a feed forward. With any mechanism, you have to add feed forward.
And then wheel diameter and wheel circumference, we just use it to convert from rotations to meters, because obviously our physics equation uses meters. So now we have this variable called denominator, which is, like the name suggests, literally just our denominator. We have this check, where if our denominator is less than 0, we're going to resort back to our initial shooting speeds for when the robot is flush to the reef, right? And obviously we need that because in the case that the denominator is 0, you're going to get a divide by 0 error. So we'd want...
And also, you don't want a negative velocity because you don't want to shoot back inside your shooter. This is something really goes wrong, which we never had. We just added because you don't want your robot to die on the field because you divide by 0, in some random place, you know.
Yeah.
Like we said, we want to be consistent.
So after we do our little check for the denominator, we finally define our initial velocity as, well, the equation, right? And then we convert this initial velocity from meters per second to rotations per second, because when you're telling your motor to fire the claw, it's going to need rotations per second, not meters per second. Or you're telling the claw to shoot the coil. And then we log it, and then after that we have our, the max rotations per second that our claw can move at. And we do this by finding the max RPM of our motor, dividing it by our gear ratio, and then dividing it by 60 to go from rotations per minute to rotations per second. And finally, we return a proportion between our calculated initial velocity and the max output, right? And that's our percentage output. So if let's say our max output is 1,000 and our initial velocity is 600, you get 0.6, and then you would use that to run the motor at 60% of its full power. And then we add Ks to account for static friction.
Yeah. So you might be wondering why we're not using a PID algorithm for this. For this type of thing, PID is extremely overkill. So we basically just decided it would just be easier to use it as a duty cycle or a percent output, if you as people might call it. Yeah, so using it as a percent output of how fast the motor can go is a lot simpler and not really necessary. It's not really necessary to use a full PID loop for something like this. Yeah, so do you have any questions so far?
So
Yes.
does your height update update, like, so from before with the elevator, like, the height updates the distance, and then that height, like, updates the velocity. So you're sending in a new height as you're moving
Yeah.
to get
So
new velocity.
yeah. So your h here would be the height of your elevator,
Yeah.
and everything here is always updating. So when your elevator is up at any moment of time, it's just always updating.
Okay.
Right? Any other questions? Yeah?
Wait, so you guys only use the feed forward controller, right?
Yeah, so we have a feed forward because we found that the way our claw is geared, if you don't add this feed forward, you're basically like subtracting from your initial velocity you calculated. And because we're subtracting for that because of friction, we're not really accounting for friction. We're missing shots. Like we're moving way too slow. So you basically, for any system, you
have
like
to use the feed forward.
yeah, for any system,
I
yeah.
was just asking, like if you guys just didn't use, like you guys only use feed forward.
Yeah, for this,
Yeah,
for this, yeah. Anything else?
How do you find that 0.05 number?
0.05. So it's, are you familiar with SysID? No, okay. But SysID, once again, it's overkill, so we didn't use SysID. So the way you find chaos manually is you basically just guess and check in a way. So you just keep testing your value until your until your wheels are barely moving.
Got it.
And once your wheels are barely moving, you basically overcome side friction, right? Any other questions? Yeah?
G is gravity in this equation, I guess.
Graph?
Gravity.
Oh yeah, gravity, yeah. So gravity is right here, and gravity is universal constant. So gravity is just number A1 right here. Anything else? Good. We'll move on. So now we're gonna go into something that's a little bit more physics heavy. Did everyone take physics C? Physics C? No? AP physics C. Okay. It's okay, it's okay. You don't have to worry about that. But we're gonna go into more on how motors like actually work. There are multiple ways you can control a motor to induce torque to actually move your motor. And these types of modes are called commutation modes. And they're basically just a way to tell you how your electromagnets in the motor. So in FRC, if you use a Falcon or if you use a Kraken, you're using a brushless DC motor. So you're gonna follow the rules of brushless DC motors. And the way a brushless DC motor works is, let me see if I have, do not have a picture. It's a oversight. But the way a brushless DC motor works is, I should. So, you basically have a rotor, which is your permanent magnet, which is the thing on your motor that actually spins. And then you have your stators, or your coils, and these are your electromagnets. So these electromagnets will basically just induce a torque on your stator, which actually moves your motor. And there are different types of ways you can send current through your stator to move your motor, which we'll get into. So the default option in FRC will be to use trapezoidal commutation. This is perfectly fine, but there are some, not even drawbacks, they're just, you're leaving performance on the table by not using torque current. So going into this, if you guys ever tune like a mechanism, you guys know about feed forward, right? You have to tune KS, KG, KV, maybe even KA. One of the nicest things about torque current is that you do not have to tune KV. KV is probably the most annoying part of tuning, especially if you don't use SysID. We don't use SysID because we try to tune manually and using physics, so we're as accurate as possible. So not having to tune KV is very, very nice for us. And you're able to, tuning feed forward is so easy with torque current that it just moves your workflow through like very fast. And I think the biggest selling point of torque current is you have much higher acceleration. And we'll get into why we have much higher acceleration in a actually right now. So yeah. Don't worry about this stuff. Just worry about, let's look at the graph right now. So they're both sinusoidal functions. Think of this as this is your torque. So this is torque over time. So your top is going to be your trapezoidal commutation. As you can see, it's pretty jumpy, and these jumps that you see are called torque ripples. And while in FRC our motors are so robust where it doesn't really matter, you still, because of these torque ripples, you're leaving performance on the table because your torque will go up and then drop for a moment and up. Like you can see here, it's not as continuous as this. And because of that, you're losing acceleration every time you go over one of these humps. Because this is a continuous function, that's the main reason why you have so much extra acceleration. Also, because it's continuous, your motors are going to be more quiet. You're able to use your current more efficiently, and yeah, almost all your current will be going straight towards torque. Whereas if you use trapezoidal, you lose. It's not as efficient as field-oriented control. And we're going to show you why it's called field-oriented control. You might think of like an FRC field, but it's just an electromagnetic field. So we're going to go into that right now. So on the left you have your trapezoidal motor, and on the right you have your field-oriented motor. So the reason why it's called field-oriented is because your magnetic reference of your rotor is always going to be aligned to the magnetic field of your stators. So basically your magnetic field is always aligned. So let's look at these. So A, B, and C is an electromagnet, and you can see you're basically, I guess, slicing the pie here, where every time you cross one of these electromagnets, you're losing torque for a minute. So if you look at the net force here, you can see it goes up and it jumps straight back down because you're passing an electromagnet. But here, all of your electromagnets are firing at all cylinders. They're always running, and that means each one is running at some sort of output, like percent output. It's a lot more complicated than that, but they're all just running together to make sure the magnetic field is always aligned to your reference. And because of that, you're able to have continuous motion like this. Yeah, so this is basically all we said. Current is always in line with torque production. Yeah?
I was going to ask a clarifying question. So for the first one, it's like you turn on one electromagnetic and turn off the other one as soon as you like switch.
Yeah, basically.
For the other one, you predict which ones you have to turn on, or you just keep them all on at all time.
If you keep them all on at all times, it's not going to move because your net force will be like
zero.
Yeah, zero. So it's setting it's setting how hard the electromagnet should pull. I guess like it knows where its reference is, and it just always aligns it so it's able to move like this. You know what I mean? Yeah. So. Yeah.
So I'm looking at the diagram right here. So does that mean it's just like a smoother calculation? It looks like the trapezoidal, it's like it's tick.
It's tick. It's basically, so it's kind of like, if you know what brush TC motors are, it's called brush because you literally have brushes going around the motor, right? So you could think of it as a tick-based method. but it's basically just a lot more smooth. Like the smoothness just helps you get more acceleration because you're not dropping straight back down and going back. Like you know what I mean? Yeah. So, yeah. Question.
You guys have code examples on the screen, like how you guys implemented the field, like that.
Oh, okay. So a lot of this stuff, it looks complicated, but it's already done for you. I think that's the best part.
It's already in the motor.
It's already in the motor. So this is a feature on CTRE devices, so like Falcons and Krakens. I do not believe it's on Rev. I do not think it's on Rev. And you're only able to use it if you have Phoenix Pro, which is a license you have to buy every year. Which is kind of predatory, but whatever. But this is just a feature you have. You don't have to know any of this math. It's a nice thing to know because you understand what's actually happening behind the scenes. But you're literally able to make this all work like, I don't know, maybe like tonight if you try hard enough. Like a lot of this stuff is not as scary as you think to actually get to work because a lot of the work is already done for you with the libraries. Anything else? Yeah.
So with libraries, like.
It's just Phoenix 6. So like you know when you need Phoenix 6 to run a motor anyways, right?
Yeah.
So are you familiar with like motion magic and how you run PID on like a
Yeah,
motor? Yeah, so
yeah.
literally all you do is just instead of using like for now I'm gonna say like position voltage, that's a normal PID PID controller. It's using trapezoidal as voltage and stuff like that. But instead of doing position voltage, you just do position voltage torque current FRC. That's what the class is called. And you basically just set your request to run the motor using this the exact same way you'd run position voltage. It's completely the same, but the way you tune your units, everything is different. Because now you're in terms of current over, let's say you're using radians per second. So your current divided by radians per second for a KV. So yeah, you're gonna notice your PID values and your feed forward values are not scaled nowhere near your voltage values. So if you're using position voltage, you'll notice that if you use in terms of current, your PID values and all your other values are magnitudes higher. So you shouldn't be worried to like go higher and higher and higher because I know it gets scary when you're running a proportional control like really, really hot. But it's just the nature of how torque current works and how current works. Yes, yeah. Anything else?
Before the season, you just decided we're using torque current on every motor. It's not like a decision you're making depending on drivetrain versus this mechanism.
It's a software issue. It's not like a mechanical issue. Like, well, I guess it is a mechanical issue because you're forced to use CTRE devices. But yeah, we basically we didn't change anything physically on the robot. We always used Falcons, and we just changed our code. That's it. So it's already built into your motor, just behind the CTRE paywall. If that was your
you're
question.
deciding that for every motor on the robot that the mechanical crew did, we're going to use this. We're not going to. You wouldn't sometimes choose one over the other.
Actually, that's going to be one of our future talking points.
Okay.
Because there are some downsides of FRC. I actually think it's the next side, so we're going to get into it. We're going to show a video first. So you can see the massive acceleration increases. Like, you're able to move up shorter distances extremely fast. Yeah, so like going from L3 to L2 was very, very fast. And that's one of the best benefits of this. But also, like, you have lower max speed. Like, it's not just like nothing in this world you get like is perfect. So what you get in higher acceleration, you lose in your max top speed, and that's what we're gonna get into. Before we get into that, we're gonna actually show our trapezoidal profile. So it hits a higher velocity, but you can see your acceleration is a lot less, right? before we get into Elevator Switcher, which shows how we actually combine trapezoidal and FOC, does everyone else have questions so far? So, going to what you said, we do choose between the two because we're able to, we want to be able to get as much performance as possible. So we're going to show how we actually use both methods to be able to just move as fast as possible. So, like we said, FOC has amazing acceleration, but it limits your top speed compared to trapezoidal. And trapezoidal has a higher top speed, but a slower response and a smaller acceleration. So let's say you're going from home to L4, you would probably want to use trapezoidal because you have more distance to actually reach your max velocity. But let's say you're going from home to L1, your distance is smaller, so you probably benefit with a higher acceleration because you move faster. And that's why using either one, just using either one or the other is suboptimal, and we're able to just switch between the two. So we're going to show how we do that. This is basically what I said. Short distance FOC is snappy, it's minimal overshoot. Long distance is smooth and it's high top speed. But this is our code. So I'm going to start with this side first. So this just is where you set desired state, just tells you what height your elevator should be at. And here we basically have a variable called fast profile running, and by fast profile we mean the one that's trapezoidal that has the higher max velocity. So what we basically do is we check, we do map, this is absolute value. We check our position, like our current position of our elevator, compared to where we want the elevator to be at. And that'll be our distance. And if our distance is greater than 20 radians, which means, like if it's, basically L4 is at, I think for our robot it's at 23 radians. So your motor spins 23 radians. Like I said before, we didn't convert to linear step points. So if your distance is like greater than 20, you would probably benefit with the higher acceleration, higher top speed, because you have more time to travel that distance, like I said. So if this is true, you're gonna run the fast profile. Does that make sense so far? Yeah, okay. So now I'm gonna go onto this side. We have two different types of, so everything we use is going to be motion profiled on the robo reel instead of the motor itself, but we run PID on the motors. And there's a reason for that, because we're able to, because we're planning to have a continuous elevator, and your feed forward values will change depending on what stage you are. But you're not able to change gains like that on the fly with if you run motion profiling on the motor, but that's besides the point. But now we're going to get into our first part of the code. You can ignore the previous velocity. That's for to calculate a derivative to find acceleration, but you don't have to worry about that. But we calculate our set point by checking if this is a ternary operator. We check if the fast profile is running. If that's true, we will calculate using the voltage profile, and if that's false, you're going to go back to FOC. You're going to use the FOC profile, and then you calculate your set point is where you want to be, and your goal is just your previous goal. And here you check if this is just a check to see if your set point is like your set point should never be negative, because home is 0 is the lowest you can be, and it should not be higher than your maximum height. Yeah, so we just check for that, and we go into our trapezoid profile at state, and we clamp it once again to make sure it stays between 0 and max rotations. This just checks if we're at the goal by doing get position minus goal position, and we do the absolute value to see if we're in the tolerance. This is nothing new. This is just like how you check for controllers at your school. So we'll ignore this for now. For at goal, we obviously stop the motors. Yeah?
Sorry, this is kind of a basic question, but
Yeah.
when you say get position, you're just pinging the robot for its location?
Yeah, so like not the robot, where the elevator is.
Oh, so
Yeah.
what position the other
Yeah,
person's
what
at.
position the
And then
elevator
you
is.
just subtract the goal. Okay.
Right, exactly, yeah. This is just a derivative. If you take the derivative of velocity, you get your acceleration. And here we check if we're using the fast profile, and if we are, we use set position voltage, and if we aren't, we use torque current. So I know this is a lot, but you could get something like this running without writing in this type of style. Like CTRE has amazing documentation on how you can get this started. But yeah, before we move on, I forgot to mention, notice how when you do, so this takes in a set point position, and it also takes in a feed forward. So elevator constants of voltage.ks get stage. Stage is like what stage you're at, but we didn't finish continuous, so it's just constant. Just thinking of it like that. So we get ks, kv, kg, ka, and then notice for torque current, like we said, you don't need a kv anymore. You just have ks, kg, and ka. It makes tuning feed forward so much easier, and it saves you a lot of time. Yeah. So, questions so far? Yeah.
How did you get the 20 radian calculation for torque current? Is that just something you were tuning over, or
So
what did you
we basically just like we could have like you could have used physics to calculate like an optimal like distance where your time is sorry, you want to minimize time. So we could have used physics, but we got like lazy, so we just felt like 20 was decent enough. But yeah, you could always, programmers like to be lazy. There's no shame in that. But if you want to be optimal, like you would probably use physics to minimize time. So you see if going at this higher speed will save you more time than going at this acceleration because the distance more, right? Yeah.
Just as a follow-up, did you ever experiment with other heights, and this just happened to be a good one, or you just stuck?
Yeah, we just we like basically the way we saw like it goes to L4 like on its own. Like everything else, torque is probably fine, but going home to L4 is the issue. Like that's where you can see the top speed will actually like help you get there faster. Right? Any other questions?
To clarify, so when you're using both trapezoidal and torque current, you have to tune your elevator twice now.
Yeah, you do have to tune it twice.
And then was there ever like the mechanical group made a change of the elevator, and then you have to go back and retune both of those again?
Yeah, both. It is more work, but I will say, yeah, tuning is just something that your software team should just be good at.
You gotta drill.
Yeah, you just gotta drill it. Like, I actually think it helps them because you're forcing them to do it more times. You're basically just drilling it in their mind. Yeah. Any other questions? Yeah.
The left side is your FRC code, and the right side is trapezoid, or is the other way around?
No. The right side is us setting the set point, like the goal, and then this, if fast profile is running, if it's true, we're running trapezoidal. If it's false, we're running FOC.
Wait, you said FOC, you don't need to tune the KB, right?
Sorry?
For FOC, you don't need to tune the KB, right?
You don't have to tune KB, right?
Okay, yeah.
We're running a little bit low on time. We might not finish your presentation, but we're gonna move on if you have any other questions. But let me see what we have. Do you want to do this? You want to do this? I'll do this. How much time do we have? 5 minutes. Okay, I'll let you guys decide. What do you guys want to learn more? Quest lab? So I think we have a few more. So we have get back, which like if you can't see the AprilTag, you'll move back until you see it. Robot tipping is like an algorithm that stops your robot from tipping if you accelerate too hard with the elevator up. Or do you guys want to talk a little bit about class and reef state? You don't have time. Huh?
I want to say picture of the answer.
Picture of this?
No, the anti-tip.
Oh, anti-tip.
What was that autopilot called?
It's so are you guys familiar with Pathfinder?
Yeah.
It's basically just it was made by a team 4414, and I guess we'll just not be as like deep into these, but we can go over this. But it's basically you have different types of motion profiles. You have trapezoid profile, you have S curve, you have stuff like this. But autopilot is different because instead of doing S curve or trapezoid, you start with trapezoid. Your acceleration is constant. So this is a velocity time graph. So your acceleration is constant on the startup to your constant velocity, but your acceleration is changing with constant jolt at the end of your profile. And jolt is the derivative of acceleration, if you guys don't know. It's the reason why you use an S curve is because it's a lot lighter on your mechanism, and we only use that for our drivetrain because what we would see is our robot would just slam into the reef. So we wanted to basically just decelerate slowly and slowly, so we lightly like love tap the reef or something like that. So it just helps us like with the slamming issue. We could have probably just like set our set point a little bit further back, but this was also a very novel solution we found to an issue. I guess if we want, gosh, oh, I didn't know how time is well, guys. Okay, we'll do, yeah?
Will there be any way we can see your slides after?
Huh?
Are you gonna post your guys' slides anywhere?
Yeah, we will, yeah. Are any of you guys going to Hawk Talks? You are? You are?
Wait, no, one more question.
Okay.
Are you gonna post that other slide?
No.
Okay, good.
Huh?
For that, like,
He's joking, he's joking. Wait, sorry?
for the what was the torque presentation?
What do you mean?
For the torque thing, you know how you
Yeah.
can install the better motor on the Falcon one? You can install like
The better motor?
no, you can install the better. You can install like the better code onto like old. You think you can do it on old Falcons?
Yeah, you can do it on Falcons. Like anything that's CTRE, I'm pretty sure you can only do it on Falcons and Krakens. But it doesn't matter how old your Falcon is. You can use a 2017 Falcon, stuff like that. You just have to use a Falcon or a Kraken. How much time?
2 minutes.
2 minutes. Alright guys, we'll do a speed run. So I guess we do reef state. So this was something that was inspired by Mechanical Advantage and RoboTigers. So they have their robot is basically aware of what's happening on the field, and that helps them in a way because the robot intelligently knows what part of the reef is taken, what's not taken, and stuff like that. So what a lot of teams do is they just have traditional auto alignment, which is goes to the closest reef, and you're basically just wasting time because that reef could be taken. So since now this year is one of the first years we're running only one driver, our operator has nothing to do now. So we decided we can make an application where the operator can just select which part of the reef is taken and stuff like that. So with this new data, you're able to run different types of algorithms to, well actually before we get into that, I'm going to show a demo of the reef being scored. So it records, the robot just records what's happening. And using this data, we're able to choose between different types of algorithms. So when we align, let's say, so this side is get a nice best score position. It just gives you whichever part of the branch is free. So So if a branch is free, it'll just auto land there. Your second one is get next with coral RP. So this one prioritizes, I think we're out of time.
Yeah.
I just want to thank you guys for being here.